Hello, and welcome to Math Science 2060, Lecture 12.6, where we'll discuss cylinders and quadratic surfaces. First, we'll discuss what a cylinder is, or what a cylinder surface is in 3 dimensions. Next, we'll talk about quadratic surfaces. And finally, we'll introduce traces, which are a tool that's going to help us to draw or visualize these 3-dimensional surfaces. Before discussing cylindrical surfaces, I would like you to recall that we're already familiar with the mathematical representations of several types of surfaces. Back in section 12.1, we looked at the formula to give the surface of a sphere. Then in section 12.5, we looked at the equation for the surface of a plane. Now, cylindrical surfaces have 2 important properties. The first is that at least one of the terms in the surface equation is quadratic. The second is that at least one of the component variables is missing from the equation. So I'd like you to turn your attention to figure 2. The equation for this cylinder is given by x squared plus y squared equals 1. Okay, so we have an x term and a y term that both have a quadratic element, or they're both quadratic terms, and we'll also notice that the z variable is missing. The result of this is that the unit circle given by this equation is simply going to be projected along the z-axis, because there's no z variable in the equation. In figure 3, the equation is given by y squared plus z squared equals 1. Again, both of these terms are quadratic, and we also notice that there's no x component variable. So it satisfies both of the conditions for a surface to be considered cylindrical. In this case, it's different from the graph we see in figure 2, since now we're given the unit circle in the yz plane rather than the xy plane, and so the cylinder is oriented along the x-axis rather than the z-axis. Finally, we can look at the surface defined by the equation z equals x squared in figure 1. Now notice that this surface does in fact define the properties that make a surface cylindrical. The x term is squared, so we have one quadratic term, and then there's no y variable included in the formula, so one of the component variables is missing. This cylindrical shape, however, is different from what you may think a cylinder to be, in the sense that it's actually a parabolic shape that's translated across the y-axis. This is a valid cylinder because it satisfies the 2 properties, but we give this one a special name, a parabolic cylinder. Next, we introduce the definition of a quadratic surface. Quadratic surfaces satisfy 3 basic properties. The first property is that there is at least one quadratic term that appears in the equation. Now that quadratic term could be something like x squared, or it could also be an off-quadratic term like y times z. The second property is that the highest order term in the equation has to be second order. So you couldn't have an x cubed term appear in the equation because it would no longer be a quadratic surface, it would now be entering into the cubic surface, a topic that we won't discuss in this course. The final property that you need to look at to identify that an equation represents a quadratic surface is that all 3 component variables appear in the equation. So, as we saw in the previous slide, the equation x squared plus y squared equals 1 is quadratic, so it satisfies that property. However, the z variable doesn't appear. And that's what's going to distinguish a cylindrical surface from a quadratic surface. Next, I would like to introduce 3 examples of quadratic surfaces that I expect you to be familiar with throughout the remainder of this course. Now, these 3 examples certainly do not include all quadratic surfaces, and I would encourage you to look through section 12.6 of your textbook for some other examples. That being said, I don't expect you to memorize all those, and going into a test, I would really only expect you to be familiar with these 3 surfaces that I present. In the event that I expected you to be familiar with another surface, I'll be sure to give you plenty of heads up. The first example of a quadratic surface I'd like you to be familiar with is that of an ellipsoid. And ellipsoids are 3-dimensional generalizations of ellipses. And indeed, if we look at the formula for an ellipsoid, we'll notice that it's very similar to the equation for an ellipse. The only difference is that we're going to include this z squared term as well. Now, recall from ellipses in 2 dimensions that each of the component terms x squared, y squared, and z squared can be divided by different constants. In the case where all those constant terms are the same, then you have the special case of a sphere. The next quadratic surface I'd like you to be familiar with is that of a cone. Now, the equation for a cone is very similar to the equation of the ellipsoid that we saw in the previous slide. The difference, however, is that one of the component parts is going to have a different sign from the other two. So in this case, the z squared will have the opposite sign from the x squared and y squared terms. It's certainly not unique to the z squared. For instance, the x squared term could have a different sign from the z squared and y squared terms, but one of those has to be different from the other two in order to trace out a cone. The final quadratic surface that I'd like you to be familiar with is that of the elliptic paraboloid. Now, the key feature of the equation for the elliptic paraboloid is that 2 of the variables are going to be quadratic, while the third component is going to be linear. So in the example equation presented here, we can see that the x and y terms are quadratic, while the z component is linear. And it turns out that the linear variable is going to indicate the axis of the paraboloid. So as you can see, the paraboloid moves up the z-axis in this case. Of course, you could also have the x or the y term being the linear term, in which case the paraboloid would move along the x or the y axis. Finally, I would like you to become comfortable with the idea of using traces to sketch three-dimensional surfaces. Now, a trace occurs when we set one of the component variables equal to a constant so that we can sketch the two-dimensional graph of the remaining equation. So in this example, we're given a surface z equals 4x squared plus y squared. As we discussed in the previous slide, we know that that surface is going to represent a paraboloid. But let's look at how we could sketch it if we weren't actually aware of that. Now, the first trace would be to look at what this equation looks like in the xy plane. In order to do that, we're going to set the z variable equal to 0. When we set the z variable equal to 0, as shown in the first diagram, we get the equation that 0 equals 4x squared plus y squared. There's only one point that can satisfy this equation, and that is going to be x equals 0, y equals 0. So in the xy plane, this surface is going to be represented simply by the point at the origin. Next, we'll look at the yz trace. That is, we'll look at what the surface looks like in the yz plane. In order to do that, we're going to set the x variable equal to 0, leaving us with the equation z equals y squared. This is simply the equation of a parabola, as shown in the diagram. Finally, we're going to look at what this surface looks like in the xz plane. In order to do that, we're going to set the y variable equal to 0. That's going to leave us with the equation z equals 4x squared. This again is going to sketch a parabola in the xz plane. However, this parabola is going to be narrower or have a higher slope than the parabola in the yz plane. If we bring all these different pieces of information together, we'll be able to determine that this is in fact a paraboloid, because in the xy plane it simply has the point at the origin, and then we know that along the other two planes we're going to get these parabolas, although one parabola is going to rise at a steeper level than the other.